start mid of as a community of computer vision researchers and aspirants who meet together to discuss research papers and then understand them in a better way. So, I mean, we share our thoughts, so it's always a good thing. So, our primary focus was so, I mean, most of us, right, we work in a lot of trending technologies in different areas and solve a lot of fancy problems, but we'll get stuck when the mathematics comes in, right? So, after that, it will be like it's like a barrier. After that, it's hard to push. So that is what our primary goal, to break the barrier and motivate the younger engineers to learn the math, understand it, and apply them into the problem and solve the problem very elegantly. So that is what our primary goal was. So we have been, I mean, successful in that for the past 2 years. We have been organizing a lot of meetups in the computer vision domain. So we started with the basic object detection problem using solving object detection problem using traditional feature extractors and machine learning, to a lot of fancy problems like image captioning, style transfer, etc., using deep learning. So yeah, so all these videos are available in our YouTube channel. So if you are interested, you can always go through it. And so we thought we took a break in between for like 3 months or so, and then we thought of resuming it with NLP now. We chose NLP because NLP is the trending technology now, and it can be applied in a lot of places, and there are a lot of questions to be answered, a lot of things to be understood. So yeah, that is why we chose NLP. And as a fresher, right, it is always fascinating to see how the computers understand the language as we the humans do, right? So that's why we chose. So for the next few months, we are going to learn NLP as a group. So looking forward to it. So when we thought of getting started with NLP, Naren I mean, we thought Naren would be the right person to get it started. Um, to give an intro about Naren, so we knew Naren as he is a farmer Soliton, so we knew him personally as well. And Naren is currently working in DA, as you said, Digital Aristotle, which is a startup who primarily focus on the NLP problems in education domain. So Naren is a person who can build the mathematical intuitions behind technology very well. So before jumping into any technology, right, we need to kind of build the intuition and understand the math and motivate others to appreciate the math. So that's why we thought Naren would be the right person to do this. And yeah, so with that I'll hand it over to Naren. Yeah. Before that, one update is so we are live streaming this session. So whenever you have some question, please get the mic and use the mic to. And the people who are attending online, please post your questions in the live chat section. So your questions will be answered in the queries time. So yeah, I'll hand it over to Naren.
Okay. Hi, I'm Naren. So, a brief background. So, I did my undergrad in computer science from Virginia Tech, the US, and then I worked for a year in Rackspace. I was just doing software engineering, and then I mean I didn't really know what to do for my PhD. I knew I wanted to do my PhD, but I didn't know in what sector. I was interested in systems. I was interested in also linguistics and also data mining, but I didn't really know much about data mining at the point. I guess more AI was more familiar with. So I started my PhD in Virginia Tech also. So, but 4 years later, I decided, okay, it's not really going anywhere, and I have to sort of come back and get a grip to with the industry, what they are doing in machine learning and other things. So I came back, and it's been 3 years now since I'm back. So 2 years I worked in a startup called Fybr. So they were in IoT. Again, that was only software development. And then I started with Soliton Technologies. I was here for 6 months. And here we were working on an NLP project with Aristotle. So we all essentially moved there because they needed more time for being consultants to manage their effort. So Digital Aristotle is a pretty interesting company. So they have a parent company called FitKids, and so they started an education by providing schools with excellent PE education and science education. So what they do, for instance, is like they have Olympic level trainers to send them to schools and teach kids and inspire them and have a really rigorous schedule and be able to track progress accurately and all these things. So they started with that, which became very successful. And then they moved into science, like so they make lab equipment, they teach the best way to teach science and everything. And eventually they decided that, okay, they need to move into the technology domain. How can we help with technology? So one of the things they do is a platform called Assessed. So they provide automated question assessment and question paper creation, question plans, what topics do you assign to students for a particular exam? How do you help them learn? So these kind of things they're trying to solve. So the problem I work at now is on math solving. So if given a word problem, how can you automatically solve it? Show the steps. Maybe show hints to the students. Can you convert that into a tutoring platform automatically? Because right now, if you look at tutoring systems like say Byju's or something, right? It's just it's either videos you learn from, or you learn from answering lots of questions, and there's really no other feedback. So can you provide much more intelligent feedback based on exactly what concepts you need to learn? So that's kind of what I work on right now. So the talk, I've titled it as a history and evolution of natural language processing. And so I am really interested in the history of things and how they began. And especially like something like natural language processing is an intersection of a lot of different concepts and ideas. Not only just linguistics, but also mathematics, like information theory, communication theory. Lots of things intersect in this thing, and most people don't have this multidimensional view of this subject. They usually think, okay, I'll do a course on natural language programming, and they get got into deep learning, and it's just text mining. And then they don't really get a full appreciation of why language processing is difficult, but also interesting, and what are the challenges. Right? So the way I've structured it is that I will first talk about the subject as it was, say, discovered by linguistics, grammarians, and so on. I'll give some insight into how we started to study language, and then once I cover that, I will then move into how did we formalize language. That is, how do we make it more abstract? So because that is one of the key innovations that happened in language, which allowed us to use computers to tackle the problem. And then I will sort of give an open-ended ending to this, because one of the things I'll go and talk about is how did the information theory influence language processing, and then eventually I'll end up with a question on semantics, because so far all of the natural language processing you do, they don't even touch semantics pretty much. Even the most advanced machine learning translation system is not going to touch semantics. So I'm going to talk about how all these things fit together. Okay, so let me just start. So this is a story that is set after the Great Flood, where you're familiar with Noah building his ark and taking 2 of every species on his boat. So this story begins after that, where humanity reunites near the river Euphrates in Babylon. And the idea, and here basically this is the only place in which humanity is now existent. So they all speak the same language, and they decide one day that they will build the biggest tower possible. And because they were all very good in construction, they built the biggest tower possible, and their goal was to reach heaven. So they start doing this, and they start building it. Everybody's working together because everybody's speaking the same language. They're all very competent at doing what they're doing. And then one day, God decides to come down and visit the city. And he comes down and he figures out what these people are trying to do, that they're trying to reach heaven. And first he thinks that, okay, if they do this, then they will start losing interest in God. That they'll be so proud of their achievements, and hubris will fill them up, and basically they lose interest in God. So then he decides that the culprit for this is essentially that they're all speaking the same language. So he decides to confuse them by giving multiple languages to people and scattering them all over the globe. So essentially he halts this project. And this is what the story, this is what Book of Genesis says about why there are so many languages in the world. Of course, this is just just an origin myth. There are many such myths in many different countries. But if we ask really, okay, how do we understand language? How can we try to make sense of why are there so many languages? Why do they all seem so different? Why is it sometimes difficult to learn a language? Why is it sometimes easy to learn a language? So this is not a new problem in the sense that we've seen this problem before, which has come up in the origin of species, which is that why are there so many species? And the answer to both questions is essentially the same. So, but the way you study it is also the same. So what you do is you start by identifying what are the parts of a species. So you say, okay, does an animal have a leg? How many legs does it have? Does it have a head? Does it have a thorax? Is it a vertebrate? Is it an invertebrate? So you start classifying these things and you build a big taxonomy based on what you think are similar. So the same thing people started doing with language. So what are the parts of a language, right? So the most basic part, the origins of language are debated on exactly how we communicated. It could have been sounds. We know sounds was definitely used. We don't know whether it could have been signs first. We don't know. So what we do know is that, okay, we can study the sounds of language, right? What are the smallest sounds that we produce? And once the writing system came in, we can study the alphabet. Then we can study the words and sentences and so on. So probably linguistics started. Okay, let me backtrack. Okay, so basically what we know now of language is that language is an evolved system, right? There was never a point in which that language just came out of nowhere. Language evolved over time. We don't know exactly how it evolved. The problem is because there's no evidence, because we only spoke orally. There's just no evidence of language until, of course, the written alphabet came, which is much, much later. So there are two changes, of course, that drive evolution. There are two factors that drive evolution, which is mutation and natural selection. So mutation is when something random gets created. So like, for instance, in a species, the blue color eyes might be randomly created, or a leg might sprout out, or a hint of a leg might sprout. Those are all mutations. In language, these are like new words that are invented. Somebody just utters a new sound, and it just and that can be treated as a new mutation. But of course, the key, the second half of evolution is natural selection. So you need sort of a critical threshold for things to survive in evolution. So in this case, enough people have to reproduce that word. So for instance, one thing, I'm probably the only person who doesn't use Google as a verb. And I don't want to use it. So, but people use it. Why did they use it? Because, okay, it just started out as a mutation, and a lot of people started using it, and it just survived, right? It just seems to be useful to use. Instead of saying do an internet search, you just say Google it. So people started studying sounds, right? So they started, okay, how do we produce sounds? So one of the things that you find in the animal kingdom is that very few animals have enough of actually the biology to actually produce various sounds like we can. So this is one. So for example, if you look at chimpanzees, they don't have the same apparatus that we do. So one of the things that people started doing is they tried to figure out to associate various sounds that we can produce with the various parts of our biology. So that includes, in this case, the tongues, the teeth, the lip, these palates, and then, of course, your larynx. So I'll give you some examples. So these are taken from a very good book which I recommend. It's called Language Made Plain by Anthony Burgess. So here are 3 examples of sounds. Okay. So this is the IPA notation. This is a phonetic notation. So these are not actual English alphabet. These are just sounds. So I'll tell you how it works. So these are put in pairs, and they're either voiced or unvoiced, which means that unvoiced means you don't use your vocal cords. Voiced means you use your vocal cords. So in this case, the 2 sounds are p and b, right? So bilabial means that you use your lips. So so in this case, bilabial is the lips, and plosive means you stop the air from coming out. So these are all consonants. Okay. So when people studied, okay, what are these sounds that can make, they found that two possible sounds are p and b. So in b, when you say it, it vibrates the vocal cords, hence it's voiced. And if you say p, nothing vibrates, but the air is still stopped. So these are consonants, and you pair them up because in both cases you use your lips. Okay. So then you can there are more sounds like that. So for instance, here you use the tongue. You use the tongue against the front of your mouth behind your teeth. You stick it up there, so d and d. And in both cases, again, it's a variation on whether you use your vocal cords or not. So alveolar means using tongue. And then the last one is the unvoiced. I mean, this is not the only ones. I've put some examples here. So this is k and g. So this is the back of your tongue against the hard palate, stops the air. And again, it's voiced and unvoiced variation. So why did people start looking at this? Because these are things that you can find in almost any language, right? So these sounds exist in English, Hindi, whatever you can imagine. Lots of things will share this. What people found is that what differs between these languages is really which sound follows which, and what is the distribution of these sounds. So I'll give you an example. So these are consonants, by the way, and this is a chart of vowel sounds. So the difference between consonants and vowels is whether or not air comes out. So if you stop the air from coming out, then it's a consonant. Otherwise, it's a vowel. So in this case, this is a chart kind of showing. So these are A, E, I, and then these are some extra vowels which English doesn't have. But they go in the middle, and they tell how much your mouth is open as you go up. And then on this side, these are O and U, again, two extra sounds which are also available in several other languages, and some extra vowels here and there. Each one tells you. In these cases, for instance, you have to like purse your lips. So you say U, O, like that. And in this case, you say A, E, your mouth is wide open. So basically, these tell you how they are arranged in terms of how closely associated they are. Right? So A and E are pretty close compared to A and I, because the mouth is more closer together. So you can sort of think of this as like a smoothness map of sounds. Okay? So people started making basically this sound map. And if you look at then what you can do with it, so here is the same sounds here, tabulated according to whether or not you use your lips, teeth, and tongue. So in this case, again, this is voiced, unvoiced. So this is don't use your larynx, use your larynx, and this one is friction against the lips and your teeth, so like that. Okay. So once you do this, you then listen to words, right? You listen to words in many languages. So in this case, Latin is father, and then in Germanic it's father. Suddenly you see that there is a similarity. And you see that the similarity is actually very smooth because the P changed to an F. Now they're both of the same class, right? P and F are the same class. The only difference is they're voiced or unvoiced. So if you go back to this thing, as I said, if a computer was looking at my mouth, right, it can't differentiate between this if it doesn't hear the sound. If it only saw the image, these pairs are very difficult to distinguish. So deaf people often have the problem as well. So if they can't hear you, they can't tell between P and B because the lip movement is exactly the same. Okay, so sounds are important, really important. But the key thing is they tell you. I'll come back to this table. But the key thing they tell you is it allows you to now start comparing words and look for patterns in whether P stays the same in other languages or does it change, or does the T sound change? Because every sound we produce is a combination of these sounds. That much we know. Because that's all we can produce with our mouth. Okay, so here, for example, is the verb to be in various languages. So, the to be is declared in various languages, so Sanskrit, Greek, Latin, Gothic, and of course you can see lots of similarities in this case. So here you can see A, as I said, is in the vowel chart below, right, and E is above. So here basically the only change is that you use a higher vowel sound. So same like that, there are lots of points. I'm not going to point out everything, and also you can see that in this case, there is another part of grammar which I'm not going to discuss, which is morphology. So in this case, here's the root word is that, right, and then here's your extension, which looks strikingly similar in multiple languages. I'll explain why this is. So here's a little joke you can make with these sounds. So here is another pair of sounds, the consonants, right? So this is P and V, or P and P, right? So these two sounds, they're both voiced and unvoiced pairs. So of course everybody knows Star Wars here, and if you now look at Darth Vader, right? So the main spoiler in Star Wars is of course that he's the father of Luke Skywalker, right? So that is the whole spoiler in the movie. Now, if you knew a bit of linguistics, you could have figured this out way back, right? So let's look at it, right? So Vader, right? We know that D and F, right? They are pairs. So so they could easily be substituted in the sense that it is possible that somebody who's trying to listen to Vader and who's not familiar with the language can easily think that you meant F rather than V. Okay, so you could substitute F for that. We also know that D and T are pairs, consonant pairs, right? So if I go back, D and T are also pairs. So you can substitute D for T, and what do you get? You get Darth father, right? So in fact, it already gives away the fact that he is the father right in his name. But of course, in Dutch, Vader actually means father. So either you know Dutch or you know linguistics, you could have figured it out. So basically, this was the start. I wouldn't say the start because this actually came a little bit later. This sort of systematic analysis of the sounds in language. So one of the very earliest sort of patterns that were discovered in language was this Grimm's law. So Grimm's were a couple of Germanic brothers. So this is about 1822, and they are famous for collecting fairy tales together, right? That we know these days, like Hansel and Gretel, Cinderella, those things. But they were also linguists. So one of the things they discovered is a systematic sound change from Latin to German. That is that if you had a word in Latin, they gave you a bunch of rules which told you how they could become word in German, right? So for instance, one of the rules is voiceless stops. So remember, voiceless means don't use your larynx. Stops means it's a consonant. Okay, so they become, he says, voiceless fricatives. So fricatives again use your teeth and lips, and voiceless again. That means you don't use your larynx. So let's look at that table, right? So in this case, why does this become that? Because P in this case is a voiceless stop. It's a voiceless consonant. It becomes a fricative, voiceless fricative. And lot of changes work like that. Not only that, but there are a couple of other rules that he described, and this seemed to be very, very systematically applicable to this shift. That basically it was a large percentage of words could be explained in this way. So this was one of the very first such laws that were discovered. Yeah. So yeah. Go on. So basically, German and Latin, they're from the same language family, Proto-Indo-European. So in this case, this law holds not only for Latin, but for other language families as well. Yeah, so basically, yeah, so there were a bunch of rules. I'm not going to go through all of them. So this is called Grimm's law. And what it gave rise to is this, not only sounds, but I'm saying including morphology, which is looking at the word endings, and also looking at pluralization and various other patterns that can be transported between languages. When you study them and look at their patterns and which one is similar, you can build a sort of a language map of the world. Now, this is only one family of languages, Indo-European. So here you can see what all languages start branching from it. So this is exactly like a phylogenetic tree in biology. Right? You should see it like that. So this is so anybody in the same sort of sibling level, they're treated as cousins, and then this is your parents, and so on. This is how you treat them. And so you can see that in this case, Indo-European through Indo-Iranian, Indo-Aryan, and then you get Sanskrit and Hindi and all the other Indian languages. Well, when I say Indian, North Indian languages, because the South Indian languages are the Dravidian family, so they are a different family. So I mean, I have for a long time heard that heard in my childhood that of course Sanskrit is the mother of all Indian languages. Of course, it's not. It's only one of the thing because the Dravidian languages are different. So again, in this case, the same thing also contains Latin, Italian, French, English, all of it. So this is a pretty big trick. And the thing you'll notice is that they're also sort of, you can geographically isolate them. So a lot of these names, you'll see that they are, have the city names in it because, these were the major population that spoke the language. Okay, so here is an example of some words across multiple languages, and you can sort of see the pattern for yourself now. So here's the father, right? So father in German, it's Vader, father in English, that German, Dutch, Gothic, Norse, Greek and Latin father, Sanskrit, very, very similar, Pitta, A becomes that. So again, you can see a lot of similarities. So this is how you study the mutation of words over time. Okay, but so if you try to think, okay, then if you try to say, okay, is the sound or what you call phonemes in this case. These are the primary sounds. Can you call them the primary unit of language? Well, you can't really do that because there are many other parts of language which don't fit into the same, it can't be explained just by phonemes, because phonemes don't tell you anything about meaning. They don't tell you anything about syntax. They don't tell you, they tell you nothing. What they do tell you is that it relates the biology of the human body to the sound mechanism itself. And of course, when writing came in, right, that's a whole different story, because you no longer have sounds. You have to think about what are the other root sort of indivisible units you can work with. So here's a paragraph from that book which talks about, can words be treated as like indivisible? So it says, so for the moment, but only for the moment, it will be safe to assume that all we know what is meant by the word, right, in inverted commas. I may even consider that my fingers typing know it. Defining a word as what comes between two spaces. That's probably one way to define it. But then the Greeks saw the word as the minimal unit of speech, so they thought it couldn't be divided. So to them too, the atom was the minimal unit of matter. Our own age has learned to split the atom and also the word. If atoms are divisible into protons, electrons, and neutrons, what are words divisible into? Right? So why do we want to study this? Because we know that certain words can be composed, right? So like if you have kilometer, you know that it's actually two separate stems that are attached together, right? So languages can play around even with parts of words. So, if you think about machine learning these days, we take it for granted that words are sort of indivisible. One approach, right? So if you're working with n-gram models, you take words as indivisible units, right? You don't care to inspect what is inside them, right? You could substitute all those words with numbers and you wouldn't care, right? So, but of course you can have character-based models in deep learning where you start from the character as your unit and you start putting things together from there. But of course there is no one way. If you're in speech recognition, your thing again would be phonemes or something like that. But the key thing you have to take from this is that machine learning, right, has learned a lot from linguistics. So for instance, in speech recognition, if you understood the physics of human mouth movements, lip movements, and sound making, and you integrated it into your model, let's say, then you would have a much better generative model of sounds. So this is the same as, for instance, suppose you wanted to build an earthquake model in Japan. Let's say you wanted to build an early warning system. So you wanted to warn people, okay, when is this wave going to appear here? Now, you would only be good at that job if you modeled the physics of the wave propagation and all these things, right? So same in this way, you can learn a lot from linguistics, like the research that they have done, and the biology, and try to encode those rules as generative rules in your model. So a lot of these kind of research has been done, but not in a large scale. This one, the sounds. No, not as far as my work. So basically, these are sort of like the problem was this was only the domain of linguists. I don't think computer scientists were interested in it probably even now they're not really interested in answering these type of questions. So, but you could. There is no reason why you can't. Like for instance, it's very easy to imagine that you could build a latent model of this mouth, of all the parts of the mouth, and then automatically just feed in examples of words, and it could automatically work out what are the movements, atomic movements.
Compression especially, they used to use that model of the...
I see, okay.
So you have a resonant cavity and you give an excitation and that produces the frequency response and based on that.
Okay.
That is used.
Okay.
But
I'm sure maybe in lip reading it might be used, I'm not sure. Okay. So because once you know that both your lips are touching, you know the class of sounds are now restricted, right?
No.
So I'm not sure though, I'm only guessing. That is, yeah. Exactly. Yeah, that was a recent article I read. Yeah. Okay, so that's sounds, and of course, so writing came in much later. So the earliest examples of writing we have goes to about 3300 BC with the hieroglyphics. Now this is actually not I mean, when I say earliest, I mean this is the earliest example of a very, very consistent writing system. That is, it had a like in this example I'll show you, it had rules for how you can put together words. It had complete sentences, they had poems, they had epics, they had everything that written in this language. But of course, like Sanskrit, it was curtailed to a very small set of the population, especially the priests and so on. So here is an example of how you start with a symbol and then you qualify it later to make it unambiguous. So here you start with a symbol for writing materials, and then you add in a symbol that looks like sort of the scroll kind of thing, and then it becomes a symbol for writing. So now you have a way you can piece together things. So the same symbol here is followed by a man sitting down, and then you know that this word is now a scribe. So you could almost call this, if people did this in speech, right? This is called proto speech or Creole speech or what. And the idea here is that when I want to communicate something, I don't have to give you a sign. I could say door, and then I could say close, and then you know what to do, right? So I can give you like bits of information. I can just keep qualifying them one after another, and give you communicate what I'm trying to say. So this is kind of that kind of a system. Okay, so and they had. But the thing with the hieroglyphics is that they did not have an alphabet. So this is not alphabet. So these are all, they had sort of an undetermined number of symbols, right? Symbols kept coming and going. Okay, so then what happened is that the Phoenician traders in about 1500 BC, they borrowed some symbols from the hieroglyphics and created an alphabet. Okay, so here is an example of the evolution of their alphabet. This is A, M, O, and R. So this called an aleph, and this is how basically you can see this evolution of the symbol over time. And this is pretty reminiscent, even in 1500 BC. So these were the first people to have this sort of a alphabetical system. So they put together actually letters one after another in various combinations to come up with a word. So this is the earliest example we can find. So here's a little, again, this is sort of an origin thing on why this word, where this word alphabet came from. So, so if you take that symbol that I showed you, the A, the symbol for A. So this is the ox head symbol in hieroglyphics. It was then appropriated by the Semitic speakers for sort of the sound A, but like more like it says like a coughed ah, right? And that this symbol is called an aleph. Okay, and then they also appropriated the word for house. Okay, this is the symbol in hieroglyphics. And this is called bayit. Okay, that's how you spell it. I'm not sure exactly how you pronounce it, but that's it. Okay, so then what happened is that, so you can see the evolution of these two letters, right? So these two letters began the first alphabet and stayed where they were through several metamorphoses until arriving in Greece. It would provide Europe with the name of this revolutionary system, and you can see how it mutated into alphabet. So it was aleph, bayit, alphabet, alphabet, and alphabet. So basically, that's how. So this is one way to also trace the alphabetical system. So we know that this word came through Greece, it came through Phoenician traders, Semitic speakers, through Greece, through Latin, through English, and then there. So again, what we're tracing here is units, the alphabet itself. So this is a bit more easy to trace than, let's say, characters. If you had just thousands of characters, it would be much harder to trace that. So, but once we had the writing system, it has its problems because, again, there are many different kinds of writing systems. So, for instance, if you take Sanskrit, it is a phonetic system. That is that there is only one way to pronounce the letters on the page, because the symbol sir is always sir no matter where it appears, right? But English is not like that because there are only 26 alphabets and there are many ways to say something. So George Bernard Shaw wrote this famous riddle that basically made fun of why English alphabet is so bad, like why there are so many confusions. So if you take, for instance, the GH sound from rough, so that sounds like F, right? Rough. And then if you take O from women, right? That sounds like WI women, WI men. And then if you take the TI from nation, right? That sounds like sh, like nesh. Yeah. Now you can put all those sounds together, G, H, O, T, I, and you can spell fish as that, right? So essentially, alphabet has this problem. So this already means that if coming back to say machine learning, if your only input is just alphabets and writing system, you already lose a whole lot of information, right? You already lose a lot of information on what is similar to what. This again goes back to treating what are the units of language. So that's just a quick overview of alphabets. There's a lot. So basically, one more point on that. So there's a lot of things that happen later on. So for instance, the Korean writing system, right? It was something that did not evolve. Basically, one guy sat down and said, "I will make a writing system," and he spent a few months and came up with a writing system, which was very organized. It had he defined all the characters, how things could go together, how things, what were the word boundaries, what you could put together, and so on. So there are ways to also come up with your own writing system, and we know it's pretty simple, right? So especially the English alphabet is really easy to come up with a new alphabet. So again, like the sound aspect of language, when people moved from one place to another, they brought in their alphabet. So for instance, when Greek monks went to Russia, they brought in the system of their writing, and that became Cyrillic in Russian. So, I guess the point also is that introducing an alphabet is not really an issue. I mean, so many languages, of course, existed without a writing system. But when we gave them, say, the English alphabet or Devanagari or whatever it is, they had no problem taking it in and integrating it, right? So again, it's just sort of the integration really depends on whether you like, and there seems to be no problem between the phonetic symbols or the non-phonetic symbols, right? So it's just as easy for somebody to SMS a message in Hindi, written in Hindi, but also in English, and it's equally fine. And we have no issues with understanding that, interpreting that. So the mind is pretty flexible. But it stands. I don't know how good the transliteration is in NLP. It might be pretty good. I don't know. So what are some other aspects of language? So I talked about the writing system, the alphabet, and phonemes. So there is also, as I said, morphology. So what happens to pluralization, all these various rules, but also things like languages which don't have prepositions, but they come up as changes in the previous word. Then there is also syntax. So this is what I'm going to talk about next. So this is what all of pretty much NLP uses now. That is, ideas from syntax are what drives most of NLP now. I mean, if you exclude any models that are trying to learn from scratch, they will try to use something from it. Okay? So obviously, if you look at these two sentences, I kicked the dog, it looks right. I dogged the kick, something is wrong, right? So we don't really know why it's wrong, it just seems wrong. And actually, if I wrote this, it would still be okay, right? You're not going to come screaming at me that you didn't understand, right? But that's the point, right? Language is incredibly flexible, so I'll give you some other perspectives on how this could be the case, right? Why we should think beyond more than just the syntactical study, but let's start with that. So, so I'm just going to read this out. This is a section from this book, Languages and Introduction. So modern linguistics emerged in the late 19th and early 20th centuries with the shift of focus from historical concerns of changes in languages over time, like we just have been talking about, to the idea that a language can be viewed as a self-contained and structured system situated at a particular point in time. So this forms the basis of structuralist linguistics that developed in the post-First World War period. So the idea here is that they try to look at language as an abstract system, especially, again, here we're focusing on the syntax, like why does a sentence look like that? They're trying to answer that question. So with regards to that, one of the very first people to head in that direction was the Swiss linguist, Saussure. And so he was also responsible for developing, him and one other person were responsible for codifying this idea of phonemes and creating the International Phonetic Alphabet. And also he was or his group of people, he didn't actually publish much, his students published a lot. And he was the first person to basically say that, okay, look, all these parts in this language, especially these root words and all these things, we shouldn't care about what they actually mean, but we should care about only the relationship between the various parts in a sentence or word. So he basically said all these little components should be treated as just signs, right? Like we do now, like basically black box entities. We shouldn't really care. So this is what sort of like sparked a large revolution in grammar studies, and dependency parsers, and all these things essentially came from this idea, and Chomsky also picked up on this. So the idea is that the relations between signs is more important than the entities themselves. That was his key thing that he proposed. So let's just take a little step back. And try to think of if we're going with that agenda, right, which is that, okay, you can treat these little entities as black boxes, right? What else behaves like language does, right? So you can think about, for instance, music, right? Music also has a very finite set of alphabets, but it also has, but of course, the same alphabet in a piano is not the same as alphabet in a violin, for instance, because again, the sonorous quality also differs. But essentially, you could create an alphabet for these things. You could create alphabet of frequencies. Then there is the concept of putting them together, right? Then there's also programming languages, right? Where you create your own syntax and you give meaning to it. Now, in all these cases, this is the key statement, which is that the class of meaningful programs, right, is much smaller than the class of semantically correct programs or semantically meaningful programs. So it's very easy to generate, say, C programs. Really easy, right? Super easy. But how many of them actually are useful or meaningful or do something non-trivial, right? So in order to study this, I'll just take a little bit of detour. So the idea here is that this was a field that emerged in the 1950s, again inspired by Chomsky's paper on syntactic structures in 1957. So the idea here is that, okay, how much can we abstract out what we observe in language, that is the structure of language that we see, can we just abstract it out somehow, like really abstract it out, not even worry about whether it's a sound, whether it's an alphabet that is making up a thing, whether it's 2 letters or 1 letter, let's abstract all out. Okay, so, and they came up with this idea of formal languages. So in a way, this is sort of really, really abstract. So I'll just walk you through it, right? So it starts out with an alphabet, which is just a finite set of symbols. And it says that a word is a concatenation of those symbols. That's all, right? And it's basically, and so let's take an example. So if your alphabet consists of A, B, and C, then the words you could make are A, C, B, 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 A, A, C, C, B, A. These are all specific words, and there are an infinite number of these words. So then the formal language says that, okay, a language based on this alphabet is something which chooses a subset of these words, okay, infinite or finite. Okay, so let's take an example again. So suppose I have an alphabet consisting of red, yellow, and green, right? Then, and I can define my language to consist of the words red, or the pair red, green, or these 3 words red, green, and red, yellow, and green, and that should be yellow, and yellow and green. So I could say that this is my language. Now, at this point, right? So there's nothing about this formal language doesn't say anything about semantics at all, right? It simply says, okay, this is the surface structure that I observe. It doesn't say how it's generated, doesn't put any constraints on anything like that. That will become the study of formal languages. But in this system that I made, we can still make some observations. Like, for instance, even though I don't give any meaning to it, you can observe, for instance, that red always seems to appear before green, right? So this is something you can observe. So, so the study of formal languages then becomes that, okay, first of all, let's step back. So the alphabet and word, right? These 2 things, we can imagine putting English into the same system, right? So the alphabet could be all your letters, or you could choose words as your alphabet. And then a word is simply a concatenation of these things, which becomes a sentence in the case of words. And you can choose a subset, which is all the correct sentences in English. But of course, there's a problem there, because how do you even define that subset, right? We don't know. So the study of formal languages concerns 2 things, which is how do you generate a word in a language? Word means the concatenation of symbols. And how do you recognize a word in the language, right? So these are the 2 things that it tries to understand. So, and you have to think about, okay, like I just said, right? There is, how do you even define all the valid sentences in a language, words in a language? Okay, so how many of you are actually familiar with formal languages? Okay, good. Okay, so I'll give a little bit. So did you follow me so far in terms of what I've been trying to say with alphabet and words? Okay. So the thing, keep in mind basically that so far we've been thinking, when I say language, right, it can be any string, anything you can put together, like English, it could be C programs, it could be mathematical symbols, it can be anything, right? So keep in mind as I go through these. So, and these two things are the key concern for formal languages. That is, if my language is now English, can I generate a sentence in English? That's problem number one. Problem number two is, can I recognize a sentence in English? Problem number two, right? And also note that this already will not tackle things like situations where I said that the boy dogged the kick, right? It won't even do that, because we know, do we consider that as a correct or incorrect part of the language, right? So we don't know. So we'll ignore that. We'll only consider what we call grammatically correct. Now, just to give a perspective on this business of this grammatically correct, right? So linguists approximate that only 60% of all the grammar rules that they have come up with are actually followed. So, so that already presents a problem in this approach. But what it does give you is a structure which can be useful. So let's just go through it and consider some simple languages. So here's a language consisting of 4 letters A, B, C, and D. And I'm saying that these things highlighted in yellow are the words in the language. So A, B, D, A, C, D, A, B, C, D, A, C, B, D, A, B, C, B, C, B, B, D. Do you see any pattern? Sorry. Yeah, starts with A. Yeah, and then the middle. C always before C. Correct. Okay, I agree with the A and D. What about the center? Any pattern there? It's either B or C, and it seems to be no particular order. Anything goes. So, can you describe this as a regular expression? Somebody? Yeah, A square bracket BC plus D, right? So yeah, so that's where the idea of regular languages comes from. So you can describe this in a very succinct pattern, which says that, okay, start with A, choose any number of B or C, but more than 0, and end with D, right? So that I've now given you a way to do part number 1. Okay, now this is generation always the easy part, right? Now suppose I give you a string like this, like a really large string, and I claim that this is in the language, and I ask you to go and figure it out, right? That is what you have to do. You have to go and write an algorithm, like a loop or something you have to do to figure out, okay, is this in this language? So what people then thought is, okay, suppose I give you another pattern, like let's say I give A, and instead of BC in the middle, I could either put BC, XYZ, and I can put many number of things, right? And in that case, again, I ask you, okay, go and write a program to recognize this. Now every time I come up with this language, you're going to have to go and write a program each time. Now people then realize that actually all of these languages had a pattern, right? That is that they could be classed under this thing called regular languages, and all you needed were a couple of operations. One is that you have letters, and you had the operation to repeat a letter, which is star, 0 or more times, and plus. Actually, you don't need plus, but star. Star is the only thing, and that's it, right? Every language of this particular form had that pattern for generating things. But the very same pattern, remember, formal languages cares about recognizing as well, because this is one of the key things, right? You don't just want to spew out valid sentences, you want to be able to recognize it. So why do we want to recognize? Let me just say why first. So even in this simple language, there are infinite number of correct patterns, right? So there's no way to generate all of them. So if you could generate all of them, you could just generate it and say, keep it in a dictionary and say, hey, look, is this pattern in here? Yes or no, right? Recognition would be super easy if it was finite, but it's not, right? In this case, it's not. So what you have to do is you need a system to work it out, right? And what they came up with is regular expressions. So not only is they gave you a way to say that, you know, A, B, C star, D, they also gave you a way to convert that into a program automatically, right? Like grep does, right? Grep automatically converts that into a program, and that program is just called a finite state automata. Right? All you need is simply one register to store what your previous value is, and a table to look up what the next state is based on the previous. So in this case, it would do the start state would be an A. If it isn't, it will automatically reject it and say it's false. Then it will have an arrow, right? The arrow will have either a B on it or a C on it, and it will go to a state, and then that state will have an arrow to itself with a B or C on it, because you can keep repeating it, and then one more arrow out with a D. As long as you follow that, you're done. And that's called a finite state automaton, or a deterministic finite automaton. Now here's another example of another language. So here there are only two things in the alphabet: open parentheses, close parentheses. And I have open close, here open open close close, open close open close, and so on. So what is the pattern? Correct. So they have to be matched, right? Everything has to have a matching thing. And I mean, I can even put, once I've closed it, I can start a new open parenthesis, right? Now, how do you describe it elegantly? Like I did A, B, C star, D. Is there a way to elegantly describe this? Okay, that's a good question. Can you describe it using the star notation? Yes. But it has to be matched. So in your case, I can't have open, close, close. So it seems like from a first try that you can't do it with that pattern, and the answer is you can't. You can go and try and prove it. But you need another way, another notation. I'll just write. I didn't write it down here. So suppose S is a sentence in your language. I can say you must start with this, open. I can have another thing there. I can close it, right? And I can have an S there, or you can go to the empty, right? So, or empty. So this means, how do you do this, right? It basically is a rule for substitution. So you start with S. You say, I want a sentence in my language. It says that it can either be empty string, or it can be this. So let's say we start with this guy. So I pick this guy. Right? Then it says, okay, I have more S's. I can go back to this rule and say, okay, what do I do? Now, I could choose for both of these S's to be this empty. In which case, this is equal to that. Right? Now, if you want this guy, the second guy, you just expand this guy back to this, and then set these two guys to empty. So you can see that all of these things can be generated with this simple pattern. So this is called a context-free grammar. So the idea is that, in fact, the only rules you need are essentially something that goes to that, or something that goes to a terminal. So terminal is a symbol in the alphabet, like this guy, right? And that's it, right? So basically, this says that this is now giving you a new class of languages. Now, again, we come back to so this is generation, right? So you can generate it. In fact, this word context here. This one? Context, no. I mean, you mean it? I don't know. I'll explain context in a bit, right? Ignore that for a second. So, basically, what I'm trying to say is this language is somehow characteristically different from this, because we said that all these languages you can describe using these pattern rules, right? Either an alphabet or a star and put them together. But this one we can't. Okay, so and I'm claiming that you need something like this, right? And this you should note is like a recursive structure, right? But then there's a second problem. We've only generated things so far, right? How do you recognize a language, right? How do you, if I gave you this, can you write a grep-like thing, which will now recognize every program like that, right? Instead of grep, it could be called CFL, right? And I give you this pattern, and it should now recognize everything. Can you do that? And the answer is yes. And the difference is that in this case, you need to have a stack. Without a stack, it is impossible to do this. And basically, what this is saying is that it's giving you the minimal machinery in order to solve the problem. So in this case, you can use a stack to pop and push things, right? So why? Because what happens, right? Whenever you see this open brace, you can push it onto this stack. If you see another open brace, you can push it onto this stack. But when you see a closed brace, you now see what is on the top of the stack. If it's an open, you have now matched it. you pop it off. And you keep going until you reach an empty stack and you're done and you've recognized the language. So if you take, say, the C syntax, C89 syntax, which is purely a context-free language, you can go basically go online, search for it, and its entire system is defined with these rules. Right? The entire syntax is defined using these rules. So this is also called a Backus-Noer form. So all the rules are written like this, and in fact, if you're familiar with a program like Bison, which is a parser generator, you simply give it this guy, and it will go and recognize the language. But of course, if you just recognize the fact that the C program is no good, you need to be able to run it. So that will add another set of complexity, which I'll come back later. So this was another class of languages. Okay, now let's try this. So consider this language here, and you have ABC, AA, BB, CC, and so on. What is the pattern? Correct. Okay, and okay, can you think of a way to describe it using either this or the regular expressions? Plus will work. How? Space where, sorry? No, in terms of like a regular expression, can you write this? Like for instance, suppose you would try this, right? Will this work? It will accept too many words, right? It will also accept A, B, B. This won't work. Okay. So, in fact, you can go and try this as well. You can try it with the stack. It won't work. In fact, you try to write this using this notation. It is impossible, and I'll give you a hint why. Right? So, suppose we try it using this notation. Okay? So you have S, and you're saying, okay, I want to start with an A, and obviously at this point I want to be able to have repetition, right? And then you could try something like this, but it will fail. Now, if your language was this, just AB or AABB or AABBB, this you can write in that. Because note that there's recursion is just inside there, right? The recursion just works. So I can write this as S goes to ASB and then S goes to AB. But for 3 it doesn't work, right? 3 or more it does not work because sort of like you have sort of distant dependency going on, right? Basically this guy wants to be 3. He wants to communicate that to this guy wants to be 3. There's no way to do that, and that's why your context comes in, right? So this depends on the context of something you produced before, something later also depends on that. Right? This quantity needs to be transferred somewhere, but it can't be done in this notation. So correct. Yes. So in fact, so coming back to the recognition question, you can't do to the stack. In this case, you have something called a linear, bounded automaton, and the only change is that this stack now becomes a finite piece of memory, which you need random access for. So in order to be able to solve this problem. Okay. So now, if you take any language like Python or something like that, all of these are actually this. But what they tend to do is that the syntax to keep the parser simple, they will make the syntax context free, and they will add the sophistication in the interpreter stage. Right? That is, like for instance, to know that I have x equals 1. Right? Sorry. Let's say I have x equals 1, and then I do x plus plus, but then I do say x equals y plus 1. At this point, the syntax should fail because this y doesn't exist. But it's too much of a pain to put it in the syntax. So what they do is in the interpreter during runtime, they'll say, okay, look, I will check this, whether this is now a valid variable. So that way they say, okay, there's no need to define everything up front. I will just do the simple thing. The advantage of defining it up front, of course, is that you catch more errors statically, but it's more of a pain for the compiler to do that. So hopefully you've kept in mind natural language as well, right? So clearly language won't fit in this, right? Clearly it won't fit in. Simple example being that I large burger or something. But then here, at almost any point, you could now expand recursively. Here I could say, I ate a very, 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 very large burger. And then here I could say, I so ate a very large burger. Like there's so many ways to expand any part of this thing, right? So this clearly won't work. Now Chomsky started from this point up. Now the thing he did is that, so Noam Chomsky, very famous linguist, still alive, and his whole idea was to decompose natural language in a recursive format. That is, he found out components of things that could repeat. So for instance, the cat or the ball, this thing, right? You have a determiner, the, and then you have a noun. So in his language, it starts like this. You have NP, VP in English. So this is one production. So these things are called production rules or non-terminals. So this is the top of Chomsky's grammar. It starts with an NP and it NP means noun phrase, and then VP means verb phrase. Okay, so this captures one of the most basic properties of English, which is that you need to have subject, verb, object order, right? So your verb comes after the subject. So basically it starts with this product, and his grammar is of course very complicated, and it's not just context free. So he adds some extra rules. So his idea is that once you generate this tree, to generate more trees, he defines what's called a transformational grammar, where he provides mechanisms to convert one tree into another tree, and so on. So for instance, you can imagine taking the tree for this, which is, when I say tree, it means that once you expand this out so that it matches this, you can now think of, okay, how could I transform this tree? Taking one subtree and putting it there, these kind of transformations. Okay, so that's, so before I get into that, so here is so this is what Chomsky did, right? So he analyzed all the various languages, various kinds of languages. This is what we looked at, regular languages. These are recognized by a finite automaton. Then there are context-free languages, which are a superset of this. They can also recognize that, but they require a push-down. Push-down literally means stack, push-down automaton. And then we saw context-sensitive. This needs a linear bounded automaton. And of course, you've heard of Turing machine. So these are your class of recursively enumerable languages. Okay, this is a much, much bigger space. Now, there is at this point, I'm just giving a very, very brief intro, because this is a very huge subject which goes into complexity theory. So for instance, all of these, right, you can also try to define how much time will it take for you to recognize something, right? So for example, regular expressions, the nice thing is it's linear in this size of the input string. This you can prove, right? So it makes sense to have even for a huge file. But if you had like terabytes of file, say of DNA code, and you try to do a push-down automaton, even then it becomes very complicated already. This is no longer a linear space; it's polynomial space, polynomial time in general to do this, right? So, and as you go up and up, you get basically the amount of time your computer spends to recognize the language ends up being larger and larger, and it's very hard to figure out how to constrain it. Now, so basically this is your Chomsky hierarchy, and I think I'll break for a few minutes. example, I'm sure or probably all of you have seen on how a natural language parse is represented. So this is called a parse tree. Ignore this for a moment. Consider this. So the sentence is, the man that came eats bananas with a fork. Okay. So what Chomsky and actually many other people since him, there are many ways to decompose it, but one of the ways in which he decomposed is based on what is called parts of speech. Okay, the first thing is that every word here comes from a single non-terminal. So this is like your S that I had written, right? So these are called non-terminals. So first thing is that you'll notice that every word comes from a non-terminal. So for instance, A is a D. D means a determiner, right? So in this case, it's an indefinite article, right? D. But the is also D, but it's a definite article. Then there are things like nouns, there's verbs, there's prepositions. And in this case, that's all that's used, but there are many more classes. And the way you organize it, so Chomsky came up with the rules on how this gets organized, right? Now, there is not just one way to organize this thing. Now, in fact, you can produce multiple different parses. I didn't put the image for that, but there are multiple ways in which you can decompose this. But basically, every part here makes some kind of a sense. So this is also, so not only is man a noun, this whole tree is also a noun, which is the man that came is also a noun, right? Because it's the subject of the sentence, right? So that is also a noun. So this is what I mean by language is recursive, and you can see why that sort of context-free grammar sort of makes sense here. Just like that, this is your noun phrase essentially, but that can appear inside a verb phrase. But so if you look at eats, not only is eats a variable, eats bananas with a fork is a variable, right? And in fact, you can make silly examples where this thing can be made infinitely larger and all these things. Like you can add lots of different words here, all these things. And basically the rules tell you where you can add what and how you can expand things. So this is what is called a constitution parse. So the idea is that all the words in the sentence are at the leaves, and everything above it is a non-terminal, which tells you the type of subtree it is, whether it's a verb, whether it's a preposition, etc., etc. Swap the? Yeah, exactly. No, that is semantics. That is semantics. In this case, eats won't work because of the plural problem. Actually, no, it does work. The man eats. The man that eats. Yeah, it's possible. It's fine. So again, that's what you. So that's an example of a transformation that's valid. So in fact, the whole point of context-free grammar is that anywhere you see a V, you can substitute with another V without any problem, which is because it's not context sensitive, right? So you can swap this V with that V, you can swap that N with this N, and everything works. But I'm not sure, I actually don't know the full details of Chomsky's grammar, whether he allows you to do that, but he has some constrained set of rules. Now, this is called constitution parse, and it's called the phrase structure grammar. That's what Chomsky defined. This is another grammar. This is called a link grammar, and this is one form of link grammar, which is called a dependency parse. So in this case, you don't have any longer these sort of non-terminals, but you still use them. Like you still have to identify that A is a determiner, fork is a noun. You still need those, but what it gives you is that it connects two words with an arrow and tells you what kind of a connection it is. So, for instance, a fork, right? You can see it's connected with this determiner. That is, it is determined. It's a fork, but it's also connected with an object. That is, this width is connected to this object, which is a fork, right? Eats. In this case, object eats the bananas, right? So this is how you link things. And the whole point of this grammar is that you know it's correct if everybody has a link. If everybody has a link, that means this according to this grammar, it's a valid sentence. Now, some word processors use this exact principle. They run this dependency parse on your sentences, and if there is a link missing, it will put a squiggly underline and say, look, something is wrong for that word. So that is how grammar checkers do one way using this method. Now, this is a lot more economical than this, but it doesn't always provide the same. They don't provide the same piece of information. They provide different kinds of information, and there are like huge number of grammars. There are attribute grammars. There are case grammars, link grammars, transformational grammars. There's loads of grammars, and each one try to start with a certain set of assumptions for that particular use case, essentially. So in machine learning, you will see, of course, dependency parse is used if you want to identify who is the subject in this, or what is this verb doing, right? I mean, which object is it related to? Right? This doesn't tell you that. Right? This doesn't tell you that. But the precise case where you said that you can swap this eats and came and you've lost the thing, right? But in this case, it tells you, okay, this is what is going on. So there are different use cases for various grammars. Now, give a little bit more machine learning perspective. So this essentially was the key to make a lot of progress in languages. So this spurred a lot of people to make databases of examples of sentences with their grammars annotated very, very precisely, parts of speech annotated very, very precisely. And because of that, for instance, part of speech can be recognized with 98% accuracy these days, right? And people annotated this. So for example, the Penn Tree Bank database does this exact analysis for a constitution parsers. Then there are databases that do dependency parsing. And once you have that, you can train your machine learning algorithm to say, okay, go and find out what these things are. And it does that pretty well. Okay, so let's just recap a little bit. Actually, any questions so far? Yeah. No, the grammars are pretty well developed for almost all languages. So, so this is another aside. So, what Chomsky showed is that when he came up with these grammars, right? Not only did he come up with grammars for multiple languages, he also came up with a grammar for grammars that basically generates other grammars. So he said that, look, he noticed that all these languages are so similar. They all have this verb, subject, preposition. They only differ in certain ways, and he was able to quantify those ways into variables. And he said that, look, I will give you this system where you set these few variables, like 10 different variables, and you get a new language. And you just set the variables different way, you get Japanese. You set the variables different way, you get English. Right? Indian languages also, yeah. So this also works for, you can work with any syntactic unit. It doesn't have to be a full word. For example, in Hindi, you will have, smaller units of the word. I don't exactly know, like roots and other things matter. So it doesn't matter, right? The tree can work in either case. Java, I'm not. Yeah, that's right. Yeah, text to see, there are many different ones. The key thing is you have to figure out what they train their model on. The bigger the model, the bigger the corpus, the better your results you'll get. Oh, is it? Okay. What is that? Do you know? Okay. So I'll put it this way, right? So his grammar is not meant to describe 100% of the language. It's meant to describe a very large proportion of it. As I've clearly shown you examples where I can garble it and still the meaning gets through. So the question really is, what was their goal? Was their goal to define the strict rules of language, or was their goal to learn, to see if there are strict rules, and then just, their goal definitely, and one clear thing is that Chomsky's work does not include semantics at all, not even one bit. So it doesn't constrain you anything about the meaning of a sentence. So for instance, I have an example, I'll come back to that. So okay, what have we covered so far, right? So that the takeaway so far is that the structure of language has been really well studied. When I say structure, I mean the surface structure, as Chomsky would call it. So there's surface structure and deep structure. Surface structure is essentially the order of words, right? And how they're extended and so on. And to a large extent, grammars have been created, corpuses have been created, examples have been created, and we can pretty well sort of decompose the sentence into its parse tree and parts of speech and so on. And because of that, we can identify similarity of languages, do translation, all these things, right? So this is what we've seen so far. But the key question is, where is the meaning in this? So what do I mean by that? So here are two simple sentences, right? So I held the dog over my head, seems simple. And then I say I held the building over my head. Of course, syntactically, they're both very correct, right? The constitution parts and the dependency part, they will both say this is a good sentence. But if, say, you were building a chatbot or something, or whatever it is, and the guy says this, and you'd be like, you should be like, what? What the, like, this shouldn't make sense to you. But, and the question really is, why shouldn't this make sense to you, right? What do we need to take into account in order for that to make sense? And so that's where semantics comes in. And people have tried, like Montague was one of the people who first tried to create a grammar based on semantics itself, that is starting from semantics. Now, I haven't put an example of that because it's kind of complex to show. There is no like simple way to show it in a tree. But people have tried, but they've failed. They've not really succeeded, right? Because there was no consistent way to integrate semantics into a thing. Because for the meaning has a huge scope, right? It can have meaning, say, logically. It can have meaning mathematically. It can have meaning in the physical world. It can have meaning in your dreams. It can have meaning in anything, right? So the domain is so huge. So again, people took a step back. I'm not sure people. I'm going to take a step back and give you semantics in a simpler domain, right? Again, going back to languages. So languages have the same issue. Okay, so programming languages, as I said, you can use context-free grammars to create your syntax. Right? It doesn't tell you anything about how variables behave, how for loops behave. It doesn't tell anything. Right? Now that comes under semantics. Now, when people initially created programming languages, there was no correct way to define the semantics. Right? Yeah. Yeah. Correct, yes. So one example would be, it would run a parser like this, and if this grammar fails to accept it, then it will put a squiggly line like that. Yeah, no. Right. So when you write it, so somebody says, okay, I've created a programming language. It's called C, and this is the syntax. And they say, go and make it runnable. Right? What are you going to do? What you could do is you could start by saying, okay, I know how to do assembly. So I will say this statement in C means that in assembly. This statement in this in assembly, and you keep going, until you say that this will now run your program. Now, you then have to prove it. That we'll forget that for now, right? That it will translate every C program into that. But that is one way in which you give meaning to it, right? And that is one of the very first ways in which people. That is one of the natural ways to give meanings to a sentence. That is, you give a concrete example of the abstract syntax that you have, right? So if I say, so for example, in gymnastics, right? If you're in a gym, if you're in the gym, right? The semantics of a statement is your actions that you're performing, right? So if I say lift the weights, you go and lift the weights. But if you tell a computer lift the weights, right? Where is its semantic representation, right? It doesn't have this word. So people analyzed ways to represent semantics in programming languages, okay? And one of the very first ways in 1960s was this idea of operational semantics, which is exactly what I described, which is, can I write, first I'll read this. So it describes the effect of each statement on a state, okay? Usually giving the post state as a function of the pre-state. Gives the effect of each statement as an operation or a set of operations on some abstract machine. So this is your virtual environment, either your assembly, your computer, a robot moving in the room. All of those are your concrete space. That is what's going to give you meaning. And your job is to convert every statement in your language to an action in the real world or in a virtual machine. So that is the point of operational semantics. So it's basically like a translator, right? Now the whole point of this is that meaning is equal to, in this case, so meaning is equal to, in this case, the action on the real world. That's it, right? Some other world you understand. You don't understand the C syntax, but say you understand assembly. That means you say, if you can tell me what this is in assembly, that means this has meaning. If you cannot do that, then it doesn't have meaning, That's what operational semantics means. That means if you can perform an operation because of this, then it has meaning. Okay, so it's very simple. So all you do is you have to create a virtual machine first, virtual environment or a simulation, wherever. It could be a robot, it could be your Android emulator. All of those are possible. Right? And the goal is to build a translator and simulate the environment. That's it. That running means your meaning gets generated in this virtual environment. Correct. It depends on the environment. In a computer, there's no way to give ambiguity. But suppose you had a robot, right? A robot environment, and you decided to communicate with it natural language. Now, you could say something as simple as, say, go pick up the book. Now, the action it takes is not the same. If it is there, it will go like that. If it's here, it will go like this. Now, those are two different things. But it knew, right? So you can build in ambiguities, no problem, right? So it just depends on your virtual environment. Of course. No, you can in a concurrent. No, in a concurrent environment, this is the norm, right? There is no deterministic way to execute, and in fact, people have created semantics just for how to reason about concurrency, right? In a sort of deterministic way, because you don't know which action is going to execute. It's purely a physical process, right? So there is ambiguity there, but what you have to guarantee is, will there be eventual meaning? That is eventual consistency. So anyway, so this is one of the very basic ways in which you give meaning. So let's think about natural language, right? And if I said, okay, can you give operational semantics for like a sentence in English? Like as the example I gave, right? Go and pick up the book, right? Now, how can you operationalize it? One way would be that if you had, let's say, a computer game, right, where that a character could go pick up a book and do all these things, and if he actually went and picked up a book, then you could say that you've given meaning to it. Now, can you do to what scope can you do that? Now, this works in the case of robots, like because they're in an environment which we understand, right? So when we give it actions, we can quickly evaluate and say, does it have meaning? Whatever I said, whatever it did it interpret me correctly? There is a way to evaluate that, and that's your operational semantics. And to what extent this to some extent has been done in natural language, in the sense, like especially in robotics, where you start with giving no examples of, you don't even teach it English, you don't give it grammar, nothing. You simply say, here is an action, perform it, and this is the input sentence for which you should do this action. And you just keep giving these examples, and it learns to figure out what the sentences mean, and it will deal with all the noise in your sentences and all these things automatically, right? Because its actions are now constrained in this world, and it has context also. So, so at any point you could give a single word, and it will know based on the context that it's built up what to do. So if I say come up, it can do the right action if it's already in a hole. It knows to come up, right? So that's where the meaning semantics gets attributed in this. So in programming languages, this usually translates to converting your code into another code that runs. And then, obviously, everything has to be mathematical, so people decided this is not enough, and decided to come up with another system called denotational semantics. So this is by Dana Scott, who won the Turing Award. This was in the 1970s, and here the meaning is given by another domain which is highly mathematical, highly rigorous, and essentially every program is one program in this other domain, right? I'll give you an example. So what it says here is that it defines a translation into, this is once again a translation, same as before, but there are some differences. It defines a translation into some functional space, usually defined in a set or a category. The meaning of the program is a relation in that space. Okay? Now, the meaning of a program is basically a function relation in that space. So, for instance, when I say 1 plus 2, this domain could have the knowledge of arithmetic, right? Then 1 plus 2 defines a precise function in that space. That is, there's a single correspondence to that. But the key thing is, unlike the previous one,
that bigger programs are always formed by composing the semantics of its parts, right? So in operational semantics, I could give an entirely different meaning to say go pick up a book, but then I could give different meaning to go based on something else. So I could say I could give arbitrary meaning to go, right? If I just said go, it could mean like burn or something. Right? Operational semantics, there is no correspondence to the parts. There is no requirement for correspondence to parts of the input to the larger input. But in this case, it precisely says that it must be composed from the semantics of the smaller parts. That means there must be some system in which when I take I went to the park, every little bit has to add up to a full semantic. I'll give you an example. So this is an example of what you could call as representation theory. So here is what happens. Okay, so so you've heard of, how many of you used types in languages, as in like int, floats, doubles, right? Have you used anything more complicated? Like in Java, have you used classes? Right? So you've used classes, right? So class is like an array. Array is a class, and it only has certain functions, right? And when I say X is an array, you cannot suddenly do something that's not array on X. Like you can't say remove the first character from X. It won't be possible if it's an array. It will only understand like go to this index, write this thing, and so on. So that is an example of a type. By that I mean that that is one way in which to represent semantics in a program. That is, if I say this variable is an array, it already constrains what this X can do. Right? You cannot add it as a number. You cannot do random things to it. Right? You have to only do array things to it. Okay. So what I've done there essentially is by specifying the type of it, I've constrained its semantics. So that is one of the very popular ways in which to constrain semantics, which is using types. That is, whatever function you write, you tell its type. So let's say I have a square function, which will take any number and square it. I can write its type like this, right? You give me a number A, I will return a number. And all I'm saying is that A is just a number. That's all I'm saying, right? Then this is now a type. Now, whatever function you write, it has to satisfy this. For example, it cannot take a number and return a string. This will fail, right? So I've specified the type constraint here. Right? You must return a number. It doesn't say which number, it can be any number. Right? Same with check positive. Right? Here's a function which says, I will give you a number and you have to tell me true or false. Now, if you tell me anything other than that, whether you take an input anything other than that or you give me an output anything other than this, it will fail. Right? So this is a way to specify specifications in a program. But like it said, right? What is the key thing? The key thing is composing. Right? Now these are two functions. Right? You can just compose them. So here is the thing. Here, if I compose these two functions where I square first and then check it's positive, the type of this also has a type, which is that I take a number and I return a bool, which will first square it and check whether it's a positive number. Okay, so this is how you build denotational semantics. Right? This is one of the ways. Right? Type systems provide you a way. Now, the extent to which you can constrain what this type can say about your program is the key problem. So in this case, I've said that I only require a number. But suppose in this type system, I said I want to require a number that is positive, that is greater than 0. How do I even do that here? Right? I literally need a piece of code now to say that A has to be greater. I mean, if condition say if A is greater than 0, which no longer is a type, which means I can't do this composition thing. So there is a huge field area on this called type theory, which tells you how you can represent any piece of computation in a type, but it's complicated. And the key theory from that is that people prove that any piece of computation has a corresponding type associated with it. There's a one-to-one correspondence. It is possible, but it's very complicated. So generally, programming languages will not be able to capture as much as possible. Right? The ideal thing is that if you could capture everything in the type, before even I run the program, I can tell you whether it's correct or not. Right? That's the point of denotational semantics. Now, this is used in the very successful application of this is, of course, in hardware design. Right? So you design your hardware like huge, you get huge circuits. Now, the whole point is you want to know, will this register ever be, say, 1? Right? Can you prove that without ever running thing? And you can if you have a system like this. Right? And people do that. So this is used in sort of proof checking. So this is used in verification. This and the next one I'm going to show you. So for instance, if I want to prove something that this driver will not fail in this condition, so Microsoft actually uses this successfully. And exactly, yeah. The next one I'm going to show you is what they use, but correct. Exactly. The next one I show you is going to be exactly that. So, so before I go to that, so let's look at this again. How would this? Now, I'm specifying this question because nobody has really considered this as far as I'm aware in languages what it applies, but it gives you an insight into how you could consider semantics, right? So this is actually a very different case. So suppose this, you consider this sentence, right? So something sat on the mat. A few minutes later, the mat was wet. Okay, so how do you give semantics to this thing? Now, the first thing that denotational semantics says, operationally, how would you do this? In the previous one, you would have an environment where you can describe a mat, you can describe a something. I mean, from something is a set of objects, and you need to think about this. But there is sort of implicit information here, right? So this is an attribute of the mat. Something has become wet, but you need this idea of cause and effect. Like something has to cause that wetness. How do you build it operationally? I don't know, but this is a little bit more easier in this case. So here you could say, so this is where say knowledge comes in, right? So if you have some way to encode knowledge, like for instance that
You use something like a
correct, exactly,
telephone.
exactly, right? So something will be a set of objects, right? A mat is an object, right? Sat is a function, right? Exactly, it's a function. And then you would have knowledge like, for instance, extra piece of knowledge like, for instance, what can make a mat wet, or what, say for example, a cat urinates or something, right? And a cat is a something, and it basically satisfies this whole thing. So again, I'm saying something here which people haven't done, right? Because but this is kind of the things you need to think about, right? How do you integrate these things? Now, there is a certain, there are certain areas in which this is possible. So for instance, if you think about automatic proof, writing proofs for a math theorem, right? Now, in these cases, this has been used very, very successfully, right? So for instance, you just give a theorem written in that language and it can output the proof.
Something X can be anything.
X can be anything. In this case, it's much more complicated, right? In this case, it's much more complicated because our concrete world is much more undefined, right? It doesn't have to be physical. It can be completely hypothetical also, but it can make sense. So there are problems. But the key thing you have to think about in denotational is, how do they compose? Now, that means that whenever you encounter this mat on its own, you need to have all knowledge about how it can behave in every situation, so that you can, when you encounter it against SAT, you can compose things, right? You cannot inject state into denotational semantics at any point. That is the difference between this and. There is in fact counterfactuals. Yeah. Yeah.
Castle analysis is very difficult.
Yeah.
For example, this is about direct variation.
Correct. Yeah. I mean, causation is a big problem. I mean, even in science, it's only defined empirically. There is no way to correctly define it, but
This is a statistical.
yes, it's a statistical thing. Yeah. So, I mean, I don't know if whether you treat it any more differently than simply a dependent variable. I'm not sure, but in these cases, I would think you would, if you had like a graph-based knowledge system where you had connections saying this does that, like triples and all those things, that sort of can be injected into this. But again, how to do it in an NLP setting while you're learning this language is the part that no one has really considered. It's possible. I don't know. Yeah. I mean, but I mean, in isolation, you can do these things. But the question I'm proposing is that essentially, that when NLP is training itself on sentences, can it train along with the virtual representation as well, so that when I give partial piece of information, it should still be able to do the right thing. So one other, the last semantics that was also defined is called axiomatic semantics. So again, this along with the previous one is used for program verification, so formal program verification. So the whole point there is, given a piece of program that you says does this, will it do that? Okay, that is the purpose of this, purpose of inventing this piece of thing. And this is actually easier to understand than the previous one, which is that the whole point of axiomatic semantics is that it tries to make assertions at every point, every stage in the program, after every statement. So assertions you're all familiar with, right? You can just do assert, one. So for instance, let's say, does the program, I forgot to write. Okay, so suppose I give you a program, ask you to write a program that reverses a string. Now, how do you define the semantics of that? One, how do you check the correctness of that? You could, for instance, write an assertion which says that the first letter in the string must be equal to the last letter in the reversed string, right? So that is one assertion, but that's not complete because you're still missing all the intermediate. But this is how you would try to define assertions. Now, axiomatic semantics defines a method in which for you to do this. So let's say here is for every statement you provide a precondition, something that should be true, and you provide a post condition, something that should be true after you finish that statement. Right? So in this case, consider the assignment statement, right? A is equal to B plus 1. That is, you're setting A equals B plus 1. And the one possible post condition is that A is greater than 1. I'm saying, suppose the post condition is A is greater than 1. I mean, I could have easily chosen something else. It depends on what you want from the program. But suppose I want A to be greater than 1. Then what should the precondition be? Right? Again, there are many choices. So one possible precondition is B is greater than 10. Because if it is, 10 plus 1, surely A is greater than 1. But is that the best condition? Right? So you want to find the weakest precondition such that it captures the most amount of input possible. In this case, the correct one will be B is greater than 0. Right? Then no other condition smaller than this will be able to satisfy more input than that. So again, that's what makes this one very difficult to actually code. Use in the real world, because it gets complicated very, very quickly, because you have to reason about these things. Now, one thing that helps you with this is you can use satisfiability solvers, which people use. So those are solvers where you say, okay, look, I don't know what this should be, but you could say, I know what it could be. It should be in positive integer. So you just say, this is a positive integer, and solve for it. Yeah, this gets complicated with looping and certain things. Like, for instance, how do you assert that this loop should finish? That's a very difficult one. Or if you're dealing with synchronous systems, how can you show that, assert that this system will remain looping forever? You can't wait for it to terminate, right? So how will you actually go? Yes, nowhere near. Yeah. No. This is not there in NLP. So I'm giving sort of a perspective from programming languages. Correct. Yes. I'm not saying you can, because I've not seen anybody use it. I'm saying that the way. So let's take an example, right? So suppose you want to write a machine learning thing that marks an email as spam or not spam. Now you could think of that as some kind of meaning, right? You're saying that the meaning of this is that it's spam. The meaning of this is that it's not spam. Now that is one simple way in which, but in that case, right, you have just two arbitrary labels. Now if you make this program a little bit more complicated, let's say you want to tell whether a sentence is talking about an animal, right? So again, you can have, it should, I mean it can. There is no restriction on whether semantics can appear or not. It's just how it appears. Like so far, right, I gave you how syntax appears. And we understand that within machine learning and outside of machine learning as well, like through grammars. Because we can define the syntax in a succinct way, but can we define semantics in that succinct way? That is, so people try to use like first order logic and integrate it with grammars to try to have a unified theory, but there is nothing that's being used with any success. Correct. But again, the thing is, how do you integrate it back into natural language? That is the.
You have to feed the machine. Really, both before machine learning as well as after machine learning. Before machine learning, it's been a format acceptable for the machine.
Right.
For example, we have to feed data in .csv like format. And the results will be in a human understanding format.
Right. Yeah.
Representation plays an important role.
Yes, that's my point here. That is, what is the representation that we can give? So one thing, again, the differences here are that axiomatic semantics does not suggest an implementation. Like operational semantics gave you an implementation, it gave you a real world. This one does not, right? So it's up to you how you actually represent it. So it's a bit more abstract than the other two. Correct. No, it can't. There are limitations. There are certainly limitations to this. You cannot do it for every possible program. That is, again, that means that can you actually do it for national language? We don't. So, again, if you consider the sentence, I won't work through it, but just think about how you would apply assertions in this sentence again. Right?
It's like in database, we use some Erwin tools for trying to hear that.
What diagrams?
Erwin.
I'm not.
Like that,
Okay.
language. So we speak something like that. Is there any language to convert that into like Alexa, Alexa?
Oh, I see. Right. I mean, I don't know what their internal representation is like. So that is so Siri and Alexa and all those things, right? They are probably one of the first things that they are dealing with semantics in a real way, because on your phone, the algorithm needs to know what is possible on the phone. That's number one. And number two is it needs to know how it maps ours to that. So it's definitely doing both syntax and semantics, right?
But parts of speech implemented. For example, I say open Google.
Correct.
So what action verbs it has to empathy? What again?
So actually what I'm heading towards is the fact that sort of a dissolution of syntax. That is, maybe syntax is not that important, which I'll get to in a second, when you consider semantics. So in that case, right, really if I'm coding it from scratch, I would not, like in the robot example, right, I would not code parts of speech. I would automatically learn it because I'm constrained by what I can do in the real world. There is no need to consider part of speech and stuff. Like open Google, right? It's so easy for it to just know that Google is an app automatically without parts of speech. So, and it will be able to deal with simply say Google. Don't even say open. Right? Now this is what we want, because we can do that, we want that to be able to do that. Syntax maybe gets in the way. So that is the next perspective. So in 1948 or thereabouts, information theory as a field began, basically because of this one person in this thesis, who's Claude Shannon. So Claude Shannon, of course, electrical engineers will know him. But he basically said that the fundamental problem of communication is that of reproducing at one point, either exactly or approximately, a message selected at another point. So his whole thesis was that I want to get some information from here to there. How do I do it? What are the problems? Right? And he analyzed that. Okay, so let's take a look at that. Right? So take a simple case of I want to communicate a yes or a no to somebody very sort of far away, right? Where my sound sort of deteriorates pretty quickly. So in that case, if I want to communicate a yes or a no, I could shout yes very loudly, or I could shout no very loudly. But the problem is that it's possible for that message to get lost. Suddenly a lorry comes by, it makes a big sound, and yes is no longer heard. So how do I make it more robust, right? I could make a system with that guy and say, look, if I want to say yes, I'll say it 3 times. If I want to say no, I'll say it 3 times in a row. And now what happens? Now if I want to shout yes, I'll shout yes, yes, yes. If a lorry goes by and the first yes has disappeared, I still communicated 2 yeses, right? So that message still gets through. So that extra yeses I've added is what's called redundancy. The yes I want to transmit is called signal, so it's signal to noise, right? So the question he asked is, what is the systematic way in which to incorporate redundancy into a message, such that you add as little as possible, because I don't want to devise a system where I say I will say yes 100 times, because if I do that, I'll spend the whole day shouting yes, yes, yes for one message, right? So you want to balance between signal and noise, right? So again, I will get to another paper that he wrote which sort of gave the statistical perspective or information theory perspective of language. So the idea is that consider these sentences, right? All these things you can understand. Right? This one you can understand, right? Even if you hear this or see it written, you can easily understand what this is saying, right? And there are so many mistakes. And not only spelling mistakes matter, but also consider this, right? So I say I entered home, closed. I'm not saying what, but what do you think this could be? Then cooked. Obviously, it could be dinner or lunch or whatever. Then munched. It could be ate, what I cooked, right? Then snored, means sleep. I don't say sleep. I say something like random like that. So in this case, you understand everything perfectly, but there is like none of these are proper sentences or anything like that, right? Or even references you were able to make, right? That the fact that I ate what I cooked, not I ate something else. I cooked specifically because I wanted to eat. Like, all these things you're getting, and again, you can see that I've transmitted so little and yet you've understood, right? So this is where the information theory perspective that he tried to understand. So this is the paper he wrote, which is the prediction and entropy of printed English. Okay. So in information theory, one of the key concepts is entropy. So entropy simply is the measure of disorder of things. So you would say, for example, a coin, an unbiased coin, which gives heads or tails with equal probability, has very high entropy because you don't know which is going to come up. But if you knew that heads will always come up, then it has very low entropy because it's very ordered, right? So so way to categorize redundancy in a signal is that you want to know if I suddenly interrupt the signal or chop it, does the message still get across? If it does, that means that there is redundancy in the signal. Because if there is no redundancy in the signal, right, then you've lost it. So for example, you wanted to communicate the number 252. If any one of those digits get dropped, you've lost the information. So that has no redundancy whatsoever, right? So, but he tried to understand. Okay, can I apply my theory to English? Right? So, so as in the previous example I gave, obviously there seems to be redundancy for sure, right? So he wanted to try to mathematically understand whether it's possible. Okay. So what he did was this. So he took all the words in English, not all, as many as there was in the corpus, and he looked at words like apple and whatnot, and he said, okay, after one letter, let's take two things. Right? He wanted to see how predictable the next letter was given the previous letter. Right? So in this case, how predictable is P given A? But he also looked at how predictable is P given AP, how predictable is L given APP, and so on. So he constructed a table where he said, okay, suppose I'm given nothing before, suppose I'm given one letter before, suppose I'm given two letters before, and so on. Okay. Then he tried to calculate how predictable it is. Okay. So what he found was that basically that English was above. So I'll just read it. I'll just read this 1 second. So one can calculate the entropy of the next letter when the previous n-1 letters are known. As n increases, the entropy approaches h, or the entropy of English. Right. So as you make this longer and longer and longer, he also did this for words. So if the sentence was, I ate something, he would take the first word, then two words, and try to predict the next one. So this is your classic n-gram. Right? So basically, as you increase the n, you will try to you will approach the redundancy in English. Right? And F0 is basically the entropy when you're just predicting one of the 26 letters plus or a space, and that's your maximum possible entropy. So then, here's what he found. Right? The first thing he found that space is actually redundant. That is, it actually decreases entropy. So in this case, look at this big thing. Right? What does it say? Right, so space is redundant. So and when you look at the score, I didn't print it out here, but it score with including space and has lower entropy than with space. Sorry, without space. Okay, so that basically says that that's redundant. And he also finds that entropy decreases as you go forward as well, as you include more and more. Right. So that clearly is a sign that you're sort of removing redundancy one at a time. So space is basically redundant and will cause lower calculated entropies when taken into account. Only in the case where no statistics are taken into account, F0, which is the trivial case where you either produce A to Z or you produce a space, is the case where the entropy is higher. Okay, so this, because it simply adds an extra symbol into your vocabulary. So when he initially estimated the entropy, the redundancy in language, he found that 50% of English is pretty much redundant.
50% is
No, this he did at the word level. Sorry, at letter level. Right? This is at letter level. So basically, he also, this is theoretically, he also did an experiment actually with people.
I'm asking why that much 50% redundant? Due to the spaces.
Not just spaces. I'm saying without spaces also. Yeah. I mean, so in fact, one of the like simple games that people play is to predict the word given only the consonants. Right? What is that word? Apple. Right? Well, one of the possibilities. Of course, there are many possibilities. Well done. So, English is bad, right? But actually, if you take Arabic, it's perfect. You don't need vowels at all, right? So, if you take like kitab, for instance, right? You drop this, there is only one completion to it, and in fact, all completions refer to a book only. So, there are some languages in which there is redundancy like that. But essentially, this is saying that you can drop a whole lot of letters and still be fine. And so 50% is quite high. So this is already saying that, you know what, something is wrong with syntax, because syntax is saying that, look, only if you form this tree, you are correct. But this is not saying that. It is saying something different. So here is so this is sort of a recent, I think 2012 maybe. This was a work by some psychologists. They tried to analyze why certain languages have particular word order, like especially subject verb object or subject object verb. Okay, and they tried to approach it from an information theory perspective. So here, the thing is that majority of the languages, about 85%, can be sorted into two categories. They either form a subject verb object, like English, or a subject object verb, like say Hindi. Right? Now, what they did was, so this is one of the things they say, right, in the paper. I'll describe the experiment in a second. So if I'm getting an idea across to you, there's noise in what I'm saying. I may not say what I mean. I pick up the wrong word or whatever. Even if I say something right, you may hear the wrong thing. And then there's ambient stuff in between the signal, which can screw us up. It's a real problem. So in their paper, they might argue that language develop the word order rules they do in order to minimize the risk of communication risk in a noisy channel. So this was their hypothesis. And the experiment they had was that, so they asked native English speakers to look at this video of basically some simple events that were happening, like somebody kicking a ball or somebody pushing a boy or something like that. And they asked whoever was sitting there to communicate what is going on in that scene. So they found two curious things. Right? The first thing that they found was that whenever they showed a person doing something to an inanimate object, the tendency was to communicate that object before communicating the verb. Right? For instance, in this case, girl kicking the ball, volunteers usually attempted to convey the object of the sentence before trying to convey the verb, even though in English verbs generally precede the verbs. Now, there was also another curious case, which is that with events in which humans act on another human, such as a girl kicking a boy, however, the volunteers would go back to the order of verb and followed by the object. Okay, so they try to analyze why this is, right? So here is how you can think about it. So suppose that the sentence is the girl kicked the boy. Actually, wait, did I miss something? First let me cover this one. So I'll ignore the case, first of all, where you have this inanimate object business, right? So because this is the explanation they give for the inanimate case. So the tendency is that whenever you have some guy doing something to an inanimate object, the idea is that you would have introduced the inanimate object in an earlier stage. So that therefore in this case, you would continue with your subject verb object order. So even if you lose the object, you kind of know. So if I say the girl kicked and then you lose that information of the ball, because of the previous context, you can fill in the ball. That is the hypothesis. But here's where the information part comes in. So suppose the sentence is the girl kicked the boy, and one of the nouns in the sentence, either the subject or the object, will be lost in transmission. Okay, so if the word order is subject object verb, then the listener will receive one of these two messages. Either the girl kicked or the boy kicked. Okay, now the problem, this makes sense, but that does not. Right? That is, I mean, it makes sense as in that you've lost information. This is not the same meaning as what that would mean if you complete it. Right? But if the word order object is SVO, right? However, there are two possible messages that you can receive, which is that the girl kicked or the boy or kicked the boy. Right? In both these messages, now the original meaning is still preserved. Right? So basically, they're saying that look, now that it is as a result of this coding problem. That is that if I code it as SVO, yeah, if I code it as SVO in this case, I'm getting a better, I'm getting my message across more robustly. So basically and this is just one example of what of how information theory can be used to explain certain aspects of language. Like if you ask Chomsky why English has SVO, he cannot give you an answer because there is no system to give an answer. Right? For him, there are no rules. All the rules he came up with have no explanation. Right? Have no generative explanation. So this is one of the ways in which we can try to give. You're saying for the grammar?
Like Chomsky's grammars give you all possible sentences, all possible combinations of nouns, verbs.
Correct.
So this is basically reducing the space of all possible sentences to more space of sentences closely matched.
So no. So the first thing you said that so Chomsky does not give you all possible things. It only gives you what.
The rules like right on the space of all possible
Units. Yeah.
They give you all possible sentences which are syntactically
What he deems to be syntactic.
and this heuristic reduces that space to give you more the sentences which are closely related to the actual.
No, this actually increases the space of accepted vocabulary. It increases the space. Yes. This is basically saying, look, even with syntax, if this accepts everything with syntax, but also without syntax, so it's a bigger space than strictly bigger space than that, because this is what we want. Because the bigger the space, the more noise we can handle. But what it's telling you is that not only can it give you bigger space, it's telling you that it can preserve the meaning in this bigger space, like in this case. Right? And it's giving you a mechanism with which it's preserving. It is that, it is that that context matters. Remember what I said before, but also that giving a mechanism of that generating that order is that. So this, I mean, information theory has been pretty successfully applied in NLP. Textual NLP. No, also speech. Everything. Yeah. There is no restriction. Probably speech applies even because, right? Think about MP3s, right? Compressing that is information theory, but you've preserved absolutely everything, right? Pretty much everything. Everything that you care for is preserved. You can do that with a piece of speech as well. And what is the compression ratio? Like a wave file is like 100 MB maybe, like a 4-minute track, and then MP3 is like 3 MB. So you preserve a lot of it, right? So clearly there are redundancies. There's a lot of redundancy there. So in that case, whether you compress music or speech, you get the same effect. And I've never compared whether you get more compression with speech or with music. That will be an interesting thing to check. Sorry. No, they're the same. The same principle. Same principle. Yeah. Exactly the same principle. It's just the method of compression varies. That is what. The way you code your compression varies. Yeah, that varies. So basically, the reason I introduced that is because this gave impetus to the statistical approach of approaching NLP. So, see, one of the things with say physical systems is that there are so many laws that help you dictate what things are possible, right? You can't do something against gravity. But in language, there seems to be like no laws. So people try. I mean, grammar. One way with grammar was the whole point of that was try to induce some laws. But I've just clearly shattered that, right? That you don't need it, right? What is the other rule that is governing it, right? So, information theory kind of seems to offer that view, right? That actually, it's really what you're trying to do. That is again, it's very coupled with meaning, right? Because the word. So if I say closed, right? The reason that closed made sense to you is because that meaning was constrained within my home because I entered my home, right? Otherwise, this whole thing breaks down. Semantics always is built into this. So people try to figure out, okay, what are there some patterns that behavior that language just sort of just maintains, right? So we already saw structural things, but what about things like this, right? So here is a well-known law called Zipf's law, and it plots the frequency of words against their rank. That is that you take a huge piece of text, go and count how many times every word appears, and you rank them. So the first word probably will be the, right? The next word might be and you then plot the frequency. This is the number of times it appeared. This is the rank. When you plot it on a log scale, you will get a straight line. So it's basically saying that this law is saying that it seems that the frequency of a word is inversely proportional to its rank. Okay, so this is something that they just observed. That was just observed. Okay, and it sticks pretty well. And I mean, it kind of fails when you go to the tail end, but it sticks pretty well over here. Now this is an example of an exponential, power law, right? So, and it's been observed in many other situations. Like for example, you have networks like social networks or semantic networks. You will find that the degree of a node in this graph will be distributed in exactly the same way. That is that you will find very few nodes with very high degree, but you'll find loads of nodes with very small degree. And people have tried to reason, okay, what is this? Why is this happening in this natural world? And some explanations are that such a graph is very resilient to noise and breakages. Again, coming back to information theory. But I mean, this is kind of a question like we don't really know. I mean, this was used very successfully. For instance, if you're into code breaking, this is very useful because, for instance, if say I garbled English with a very simple cipher, I just substituted every letter for some number, right? And I wrote a message and I did this and I gave it to you, right? And I kept doing this for a long time, for over a year. I sent you hundreds of messages and you're trying to figure out what it is. Right? The easiest way is to simply go and plot the frequencies of all those numbers, right? You will now get this graph for this also holds for letters. You will get the same graph. Now you know what the first guy is E, because you know that in normal English E is the most big, right? So I mean, it's used in those kind of cases. And there's another law that might be interesting, like Benford's law, which applies to numbers, like the distribution of numbers, and then the last digit of a number, it applies. Exactly. So this is for finding fraud detection in transactions. So there are only certain patterns of a distribution of numbers that appear in the last thing. So suddenly, if you try to like siphon off money by like taking 1 cent from lots of bank accounts, they can figure it out just by this. But anyway, so again, I don't know. So I mean, natural language processing is very varied, right? It's not just about translating one sentence to another. It's not just about giving semantics. Sometimes it's something as simple as this, right? You want to just break a cipher, or you want to do something else, or you want to classify spam, not spam, right? So, so Chomsky had a problem with this, right? So, this was a speech he gave in the 150th I guess you call it anniversary of MIT, and he was talking with Peter Norvig, right, an AI researcher. So he basically had this to say about all the statistical models. He said, it's true that there's been a lot of work on trying to apply statistical models to various linguistic problems. I think there has been some successes, but a lot of failures. There is a notion of success, which I think is novel in the history of science. It interprets success as approximating unanalyzed data. So he had this thing that, I mean, Norvig has a huge essay on this, right? He tries to figure out what exactly does Chomsky mean. So basically, his thing seems to be that statistical models doesn't really give doesn't really tell anything about the language. But again, if you think about it, Norvig argues that even his thing doesn't give any meaning. So, and he claims that there have been successes but a lot of failures, but he fails to see that there have been a lot of successes as well, and Norvig tries to describe all of the various successes in this thing. But I think maybe what Chomsky is trying to get at is the fact that there is no interpretation of the language as we do, like the semantics, right? The way we interpret it, I'm sure he's not happy with that, or he thinks maybe statistics is not the right way to go. For instance, he once famously said that there is no meaning to assign a probability to a sentence, because his thing was, I can invent a new sentence anytime. Right? I can invent a completely new sentence that has never been observed in the history of the universe at any time. And he thought it's just completely ridiculous to apply a probability of that, but we know we can, and it's not difficult. and it has meaning to apply a probability to a sentence as well. So, I mean, there are some arguments, you can go read that. It's quite interesting. Yeah, yeah. I think maybe he was going for this, trying to solve all the problems. So I don't know how much time do you have done now? Okay, I will just do this one part. Try to give a quick overview of one of the main problems that NLP solves, or tries to solve, and probably succeeds in some cases, does not succeed in other cases, which is that in language, the key thing is that not only do you need to be resilient to noise and other things, but you also need to learn. That is that, when I introduce a new word into this into a sentence, that you need to be able to pick up what it is without having to consult a dictionary or having to retrain a model or do anything like that. Right? So take this example. Right? So you have Rohit took his hat off. Let's say you've trained with this example. You've also trained with Fatima took her hat off. Then Rohit took his shirt off. Like, you have these sentences, right? And then here's a sentence completely new that you're giving to this model. It says Gretel took her hat off. Okay. Now, for me, there is no problem, because even though this is a new word, even though, let's say, I mean, I've put a proper name here, but suppose I just put some garble there, there's some random letters here, took her hat off, I'd still be okay. Not only that, I now have associated that her goes with that I've ascertained the gender of that. And basically, I can now work with that word as if it was part of my vocabulary in the next sentence, and I can continue with that, right? But not only nouns, I can do that with verbs also. Like, I've just introduced a new word here, like Gretel, she took her hat off, right? And I just continue to say, and Hansel caught it just as he came in. Now, what does that mean? What does this mean? What is the meaning of this? True, right? So there is really, right, we can so easily, right, understand that. Now, almost no NLP model will be able to deal with things like that. So the thing is that if you take, so say speech converters, right? So models that try to convert speech and do closed captioning. So in those cases, oftentimes people introduce new words into the system, right? Like, I talk about a new thing. Like in this case, I'm talking about that. What will closed captioning do in this case, right? There is no way in which it knows the part of speech tag for that, because it's a completely new word, right? How will it be able to integrate? And if I've just used, and will it be able to infer the fact that, for example, this is now means throw, right? And it can't, because there is no. That is, if you think about word vectors in this case, right? Will it be able to assign the same word vector as throw to that one? Yes, exactly. So, exactly. So there are models which are specifically geared towards this. There is, I'm talking about a whole integrated model being able to deal with this. So, for instance, like people add extra pieces of apparatus to, say, machine learning thing, where they say that I will keep in memory the last 20 words that occur, and then whenever I'm reading a new sentence, not only will I use my existing vocabulary, I'll now play with this also. I can just stick that in. So there are many ways in which you can incorporate it, but this is one of the simple examples I'm saying. I mean, there are many ways in which I can just drop context here and do all sorts of transformations where you will understand it, but you can make the machine think. So Google Autofill probably a little bit simpler in the case of how it completes. So that's more, you can do that very well with an n-gram model itself. But I'm sure they do more sophisticated things. So in that case, of course, you want to complete things that are more recent as well. So they have other pieces of it. So when we think about how NLP will deal with this, if you go for like a purely syntactical approach, you're not going to get anywhere with being able to deal with these. Now, information theory approaches, i.e., that also includes probability, give you more of a apparatus to deal with these things, right? Because whenever you're defining a word, you always define it with respect to what it comes around. You don't treat that particular word as like a holy grail. So you'll be able to go forward with that. Now, there are lots and lots of techniques that we can do. So once again, I've sort of reiterated what I mentioned before, which is that things like these become easier when you have an operational domain to work with. Either you have some knowledge that restricts what is possible, such that whenever these things happen, you try to associate everything to a real world, right? You try to associate everything to an operational domain. If you're able to do that, then you can deal with it. So consider this case, right? Again, you have a robot that's navigating, and it's learned to figure out that go forward and get me the book means go forward and get me the book. But let's say my friend comes in and he is not very good in English, and he says, "Hey robot, go aage and get me the book." Right? It can deal with that, because really the only one way to resolve this is to go pick up that book. It understands this, it understands that, it understands go. Now it needs to fill the gap. There's only one way to fill the gap, which is to go there and get it. Right? And by doing that, you've now reversed, you've sort of fed back that input and saying, actually this means that. Okay, so word vectors sort of get you to that space, because their whole thing is that once you represent words in a very smooth domain, right, like in a vector space, then other new words can sort of fit themselves into any part of that system. But the way you do that, exactly like that. Yeah. Which one? No, I'm not saying there is a system that does this, but I'm saying it should remember it the next time. Yeah. It can either remember it for short term or long term. But the nice thing is it doesn't have to remember, because the next time it will still work it out, right? The same thing. I think I'll probably stop, because I was going to go just give some explanation, give some continue on this theme of essentially how to make room for the unknown. I've called this because you will see unobserved words or unobserved sounds. You will see new letters. You might see new spelling. How do you account for all these? Essentially, I was just going to give a little bit of overview on where this all started, right? How do you give? I'll just cover maybe this slide. So, how many of you are familiar with just basic probability? Okay. So let's say you observe either, let's say in a sentence, right? You have loads of sentences, and you look at, words that appear, and you look at what was preceding, right? And you try to learn what is the probability that this word will appear given this guy appears. Now, let's say that the word is, some of the things you learn are, let's say apple comes before, and then you find that computer follows. Then you say apple comes here, and something else follows, apple tree, right? But let's say here you don't see this, apple laptop. So you see these two, right? Now if you consider probability distribution, normally you model this thing as a multinomial distribution, right? You say essentially all these dots, they have a frequency, right? I have a table of frequencies. For every dot I have a frequency of the number of times it appears, and you say that multinomial distribution is, right? So you have these probabilities, right? En. Let's say there are n dots. You have n words. You have all these probabilities, and they all add up to 1, right? Now, the problem is that whenever you have a new word, but let's say even if this word is recognized somewhere else, say laptop appeared here, but not after apple. So let's say that Pn is laptop. Now, one of the ways in which to get the probabilities of a distribution is you need to estimate the probabilities, right? So one of the very popular ways is simply to do a maximum likelihood estimator, which is to simply maximize the multinomial function with respect to the corpus, right? In this case, this appeared 0 times, that appeared this time, this appeared that time. When you work out what the formulas are, you will get that the probability is simply k divided by n, where k is the number of times a word appears. But what will this say about laptop, right? It will say, what is the probability that laptop will appear after computers? It will say 0. Right? So this is the basic problem in probability and NLP, all deep learning, everything works in the same principle, which is that how do you, in any sort of meaningful way, assign a non-zero probability to this? Because every sentence should be possible. It can't just be the examples I've shown you, right? Everything has to be possible. So there are loads of methods. I'll just leave this slide here. There are loads of methods that people came up with to essentially take out this zero probabilities and to smooth it somehow, in some meaningful way. So one simple way, the first one, right, is simply to just assume that anything that has not appeared has already appeared once. Just assume that. That is one way. But it's not a very good way, right? Because it doesn't differentiate that, if let's say laptop doesn't appear but also cat doesn't appear, it will predict both to be the same probability, which is silly, right? Yeah. In that case, there you have already observed the head, right? So I'm talking about the case where you have something completely new. That is, you're trying to predict the probability of everything that you've not seen. So can you meaningfully assign that? That is the question this thing is asking. So basically this one is one of the most popular smoothing methods for n-gram models, and essentially for a very long time, only until recently, n-gram models smoothed using this system was pretty much the state of the art. Right? These are all probabilistic methods, yeah. Yes. So this one is the Bayesian method. These are all.
How do you approximate the number of apple or on what basis
there are many ways.
Historical data?
No historical data. No historical data. It's based on some assumptions that you make. So like this one, right? I said just add 1 to everything. It seems like a reasonable thing, but it's not very good. But there are other methods. It will take a long time to explain. So
Which one is more effective among these?
This one is the.
What it does?
So n-gram models you're familiar with, right? N-gram models.
Yeah.
So the state of the art, which is not deep learning, uses 3 gram, 2 gram, 1 gram models. So basically, this one takes 3 contexts into account, 2 contexts into account, 1 context into account, and 0 gram.
Like a phrase.
So it builds your normal counts for all these n grams, and right. Suppose I have I ate A, right? This is your 3 things you've seen, and you want to predict this one. Now the bad thing to do is to simply trust this guy for what this next word is, right? Because in your examples you might have only seen I ate a banana, which means the only thing you can predict is banana. That's bad. So what this allows you to do is that it allows you to take information. If something is not available here, it allows you to smooth it using that. It will say, okay, maybe you can use that piece of information to give you some hint on what this should be. And then if that doesn't work, you go back down here, and it moves. And this works really, really well.
You use something like the Bayesian method.
So a lot of these can be derived from Bayesian methods, but there's really no need to. I mean, you'd have to invent a proper conjugate, like a distribution and all that. So that's more work. You can do it. I mean, people have done that. But yeah, that's the general principle. So this used to be the trigram model with Bayesian smoothing used to be the state of the art.
To find out how much is the frequency of that particular word, right?
So I'll tell you the beauty of this, right? This, you can download the program today, right? And it's incredibly fast to compute, right? Because you're just doing counting. You're just counting all these things and applying smoothing. There is no like extra learning. You do the same. To get the same amount of performance in a deep learning system, you'll have to train it with a lot of data. And, I mean, this also needs lots of data, but it needs to do all this like representation.
So make it possible to
Yeah. If you had loads of data, this is. Yeah. So I think I'll stop there. Questions? What is that? Yeah. So again, it depends what you want to use it for. So for instance, suppose you consider morphemes, which are the pieces of the word, as basic. Now that's not very useful if you want to understand, say, rhymes. Because to understand rhymes, you need to break it down by syllables. So really it matters like what your context is, right? Whether you want to understand the grammatical meaning, whether you want to understand some other meaning, all these schemes, right? For example, to understand so much of the, say, the structure of poetry or other things, you need to break it down in different ways, like meter, rhyme, all these things matter, right? No, because you can't create syllables from phonemes.
Is there any
That
method
is
to understand the intent of the word spoken? For example, mother is in the kitchen, bring waters, he is telling.
So maybe for boiling or for
Correct,
vegetable cutting, cleaning, something like that.
So these are what these are.
Or context, which context he represents.
So these are
Something.
this is called in general word sense disambiguation.
I think some tools like Siri or Alexa should understand the
Yes,
context.
They need to. I mean, to what extent they do, I don't know, because I don't know their algorithm.
Okay. Is it context aware systems are very hard, right? Building it, and what type of methods could be used in building
So
context aware?
again, I think it probably helps if you start from a domain that you understand really well. Like for instance, you say I only want to work in the medical domain, then you could figure out what are the possible contexts in a medical domain. But to do it in general, I think is it requires knowledge. Yeah, it needs somewhere to. No, he's talking about the knowledge of context, right? So it's okay, it can learn these words, but will it also learn what is the appropriate situations in which this word is used? And when you don't provide this word and you only provide the context, can it deduce that this is what needs to be used?
Images can also be so. I mean, searching also.
Showing the images can also help the people to still go higher. Maybe elephant means different colors of elephants are there. So showing that can help them to choose. So combining, even in the future, maybe search may be combined with images, not only keywords. So the intent may be visually seeing and giving maybe much better method. Yeah, because understanding is better facilitated through images, visual perception.
If you think about it, words to describe very complicated things came much later than simply being able to point. So I can point it and then I can continue a sentence. See, that is a big bottle of water. But I don't need to invent a word for that. I can just point. So like you're saying, images help. If you just take image.
Companies are using waiting for intent.
Any more questions?
I mean, into the specific techniques for NLP, would there be any other follow-up session or?
I haven't planned it. I don't know.
Okay, because I'm a beginner, so I was looking at more at what are the actual things over there. And regarding the amount of computation required, right? I mean, let's say for a standard application for machine translation or whatever. So, I mean, what is the typical scale of computing power needed? I mean, can you fit it in a device, or do we need GPUs?
So generally, inference with deep learning, it's very cheap. Inference is cheap, inference of an example is cheap, but training is expensive. So for that, you need training. You need loads of things. But once you've trained it, you can put it in a phone.
Oh, okay. So a normal GPU is sufficient.
Yeah. For which? Anything? I mean, there are just. I would just recommend doing one of the courses, like either the Stanford. What is that? 224. Yeah. I think there are a bunch of other ones. DNM. Yeah, there's one for deep learning and there's one for normal one. I think that's a pretty good course, and it's very up to date. So you can.
NLP and deep learning are related.
They're not. I mean, they're separate. They're separate. Yeah. So all of the things I described. See, these things are all without deep learning.
What deep learning adds to
Well, nobody knows what it does, but it does well. It does very well. So I don't know. That's what. No. So see, probably the applications in which only deep learning has been successful is things like, for instance, you show a picture and you have to describe it in a sentence. Now this, as far as I know, only has been done in a deep learning context. Now, having said that, the only reason it's not been done in a probabilistic context is because there is no compositional way to create very complex probabilistic models until recently, which is called probabilistic programming. Like just like you can say, give me this layer, this layer, this layer in deep learning, there is no way to say, give me this distribution, this distribution, this distribution, put it together. But now people are starting to do that. Once you have that, there is no difference between deep learning and this one pretty much. So in fact, calling it, I mean, see, just because you have a probability model doesn't mean you have something that's explainable. That's not right. I mean, they're the same thing, right? So if you want to call a traditional probability model, the whole point is it's a generative process which you understand. Like, for example, I didn't cover it, but this you can take a look at. I described context-free grammars, right? Now there is a probabilistic version of it, which simply says, okay, I will assume that my language has a grammar, but I don't know which one. It could be many things, and this will learn that. So this is used for things like the part of speech tagging and a lot of other things. So this is what I mean. So this is something that's explainable because it's giving you this tree, right? It's telling you, a verb comes here. But again, I mean, explain is a very loose sense. I mean, so I had one example here, so I'll just leave this up. So if you consider computers that play chess or Go or whatever it is, when they make a move, right, you can ask it why you made the move, and it can tell you exactly why it made the move. No, normal, even searching, right? Because this is normally a search problem. Even in deep learning case, it can do it because it knows how to compare two moves. And it can tell you the difference between the move. It can say that if you make this move, the knight will take you, so it's bad. If you make this move, now can you do that in NLP? Right? Can a thing that says, okay, look, I'm choosing this word. I'm saying I ate the mango because I can only eat mangoes. I cannot run mangoes. I cannot walk mangoes. Can it give?
So we can do reasoning without deep learning also.
Yeah. What is the word? Exactly. Yes, that's precisely the point. Now, exactly, that is where the semantics comes in. That is where things like the operational domain comes in. Where are you operating? Now, you have reward if you're doing NLP in a robotic context. Right? I want language for it to perform action. Now, it knows when an action is correct or not. Now, that's the point of having semantics. Right? When you have semantics, you can give a reward. Right? So, and it just is an example of perfect information. Now, you can have the same thing with poker. Right? Even if you have poker where you have hidden information, it can still give you reasons. It can say, I chose to bid this much because I believe that guy has this many things, because that's what probability gives you. It allows you to reason even in an uncertain context as logically as you would in a normal context. But still, the problem is in NLP, it's harder. There's probably something that's been done. I'm not sure. I'm not sure what has been done with respect to reinforcement learning and natural language. That might be interesting to check, but that would be the kind of area.
Learning is about learning by itself over time.
Yes, but with some response from the world. It needs feedback. Yeah, it needs feedback. Sorry, say that again. I didn't hear. Correct. What are the rules? What are the rules here in language? But how would you explain the things which have no syntax, like this one, right? This one. These things, or that one. No, but probability is not an explanation, right? So you need to give me an explanation, right? So even in poker, you make an action based on the beliefs of the thing, beliefs of the state of the world. In this case, yes, you can believe, but how do you communicate the fact? Right? How do you communicate the fact that, will it communicate to me that this munched, it can say that it meant ate, that's fine. But can it then say that I ate what I cooked? That I really ate what I cooked here? Right? Can it really resolve the context of this very finely? Right? That there is no one true answer to this. Right? In poker, there is really one correct action, one or several. In this case, you could just stop it saying, okay, look, I cooked something, I ate something. I don't actually have to say I ate that thing, but actually I'm probably implying that. Right? So there is no one correct outcome that you expect in this case. Representation of, let's say, You can. But once again, there is. It is there, right? The disambiguation is there in this context because this is what generally happens. Yeah. Correct. In our context, it works. So, I mean, of course, there is nothing stopping you from saying that I will also give you probabilities on a relationship between words and things. You can keep building larger and larger things, but what is the end to that, right? How many more rules will you say? How many more rules for explanation will you incorporate into the system? Right? In poker, there is really only that one objective that you need to do. All the actions are now evaluated against that. So in this case, it's not entirely. I mean, I don't know. You might be interesting if you find out a reinforcement way in which language is learned. But I mean, in the end, you have to think about this is another thing I didn't mention, which is that language only exists. Would not exist if I was the only person. It exists purely because I'm going back and forth. I'm going back and forth. Like I'm always communicating with another person. I always have an audience. But almost all NLP doesn't have an audience at all. That is that. What is the audience? Either its audience is its own virtual environment, or some world that is hypothesized, but there isn't. Or it has to be like a target language that it's translating to, but that doesn't really tell you anything about the meaning of the sentence. And only now people are trying to only now people are doing chatbots where communicating back to the person. Only then you really get to understand what the computer knows, right? Only when you get back. And because it's going back and forth, so much of syntax doesn't matter. It's about how much context can you keep, how much do you understand about this one word I say in this particular context, right? So all those things sort of come into play. And in that case, probably reinforcement learning is sort of an interesting thing to think about. I don't know. So yeah, I mean, it's entirely possible to imagine that to write a reinforcement thing where or many people sit with a computer knows nothing, and you set up a reward system, and you just talk to it, and it starts giving you garbled things initially, and then slowly and steadily it can start improving. It's possible. I've not seen it done.
Actually, we haven't decided what is the next session would be, but so we are planning for both of them. Actually, we'll build up. So that is how we plan, right? So today also it is introduction session. So next would be something related to conventional way of doing it, and slowly we'll introduce deep learning into it, and then go take it forward.
Sorry.
Yeah. Yes, group meaning you are talking about the Bangalore Computer Vision meetup itself, or our. Yeah, so actually we started as a computer vision meetup. It was Bangalore Computer Vision meetup. So the last 2 years we have been organizing meetups in the vision area mostly. So we started with basic object detection problems, right? Like human detection phase. Yeah. Okay. So. Yes. Actually, as we are getting started, it is like that. But our ultimate aim is to go to that level. Actually, we mix and mash both of them. We organize sessions which are application oriented, and then sometimes we mix sessions which are really mathematical. We just go deep into the mathematics and understand what is happening inside under the hood of the technology. So it's mostly mix and mash of those kind of sessions. Yeah. Okay. Yeah, that I agree to that, but yeah, sure. So So the thing is, mostly you can find those kind of things in online courses, right? So you can just take a course and then understand all those. Yeah. Sure. Yeah, thank you for your feedback. Actually, we try to keep those kind of sessions as well. Okay.
Meaning of chatbot, which is bad, right? Luckily, some hype has come around AI. Now, this is the time we have to say put people in the right track. I mean, the chatbots. I mean, chatting is there from ages, and some difference you have to see. Right, right. And I think very good people. to some decision. Is that, I mean, is that level you really work?